Okay, good cue to get started. So welcome everybody. My name is Scott. Welcome to the summer iteration of the Path and ECOS seminar. So as you probably would guess, these are not recurring regularly, right? They'll just be kind of ad hoc. So thanks for coming today. Stay in tune with your email because or Slack or wherever you get your notifications because there'll probably be more in the future. But today I'm going to introduce current PhD student, soon to graduate summer.
Yeah.
In summer.
Yeah.
Yanglan Wang, who is actually very, very interesting background. I find it interesting. So a PhD student in civil environmental engineering and systems engineering, primarily advised by Kenichi Soga, but also collaborated a bit with Maria Loa del Monache, and actually has been doing a lot of work in traffic flow modeling, simulation. And, it's interesting because those of you who know Kenichi Soga, that's not exactly his core area, but he thinks a lot about, for example, disaster response and things like that. So Yanglan has been thinking about how do you manage traffic flow if you have a community that's trying to exit an area where there's a choke point. And so he's gained a lot of experience in those things. But before arriving here at Berkeley was, master's degree at Tsinghua in control engineering. And then before that, bachelor's degree at North China Electric Power University. So it has kind of this electric power background as well. So an interesting mix of degrees. So, I've always been impressed with my conversations with Yanglan. And I don't think this community has had a chance to see a lot of her work. So very excited to have you here.
Yeah.
Thank you. Go ahead.
First, thank you very much for Scott's great introduction, and also thank you very much for all of you taking time to listen to my presentation. I feel excited to share my past work and also my thinking about the future work with all the audience, whether you are in Zoom or in person. The topic of my presentation is traffic simulation, optimization, and control from macro to micro scales. So if you have any problems during my presentation, feel free to interrupt me. I will explain my contents from 5 parts, including background. And next is the first project that I did during my PhD, optimal control modeling for switched systems in traffic simulation. I will put more attention to explain this project. For the second project, a link-based mixed integer linear programming for traffic signal control, because of the limitation of time, I will just introduce it briefly. Next, I'd like to share my thinking about future work, and finally is summary. First is background information. When I started my PhD, one question was always in my mind. That is how to conduct large-scale traffic simulation, optimization, and control efficiently. I think this question is very important because numerous applications in our daily life, including commute traffic management, traffic signal control, traffic boundary control, and even evacuation planning, all these applications use a very similar simulation or optimization method, although they have different settings based on their applications. On the other hand, I think it's very difficult to realize efficient simulation, especially for optimization, because it involves large number of traffic variables, complex problem settings, and high computational demands. So how to solve this problem? I try to solve it by exploring 2 projects that I did in PhD. The first project is optimal control modeling for switched systems in traffic simulation. In case you are not familiar with optimal control model, I want to introduce the general concept briefly. The optimal control model has an objective, and it also has state dynamic formulations to describe the system dynamics, the state and action constraints, and the endpoint constraints. After we define the model, we usually discretize the problem by using some numerical method. And then we solve this model by using the numerical method. The numerical method usually starts from an initial solution. And then according to the direction of a gradient descendant, we can always find the local minimum or global minimum if the problem is convex. After we find this X star, F star, and then we can say we solve this problem by finding the optimal state and the control. This is just a general concept of this method. Why do we choose this approach? The motivations come from two parts. The first factor is that this method can ensure exact dynamics. There are two types of simulation method in traffic area: the microscopic traffic simulation and the macroscopic traffic simulation. For the microscopic traffic simulation, it creates dynamics for each vehicle, as this figure shows. So you can see that this traffic simulation method is not very suitable for large-scale problem, because for the large-scale problem, the number of vehicles will be very large. So if you want to solve this system, the number of variables will also increase accordingly. So in this method, in this problem, we chose macroscopic traffic simulation, which creates dynamic for links, as the figure shows. So it can capture the aggregate behavior of traffic flow. Sorry. The reason why I chose this microscopic simulation method is that even if for large scale traffic simulation, the number of variables will remain stable, because the number of variables is related to number of links and will not increase according to the rising number of vehicles. The second factor comes from the optimization method. I chose to use gradient-based optimization method here, which can ensure mathematical precision, because in traffic area, the previous researchers already provide very accurate traffic dynamic formulations. So it's important to ensure mathematical precision to satisfy this physical information to ensure safety. There are also other researchers use heuristic algorithms, including genetic algorithms, simulated annealing, and so on. These heuristic algorithms try to find a better solution compared to the initial one by using some techniques like mutation or reproduction. So the heuristic algorithms just find a better solution compared to the initial one. It cannot guarantee the global minimum or local minimum. But it also needs longer calculation time compared to gradient-based method. The third method is a neural network-based optimization method, which is very popular recently. But at the time when I started doing this project, maybe 3 years ago, the neural network-based optimization method is hard for them to satisfy the physical dynamics and constraints. But now, some researchers say, oh, they design some special structure that can ensure such dynamics can be satisfied. Maybe it is also the direction that we can explore in the future. This slide is a general formulation for optimal control, which is used to find a control U for a dynamic system over a period of time from T0 to Tf, such that an objective function is optimized. So this model has an objective function and it has a dynamic formulation and the constraints. I just draw a very simple network here. In our model, the control U is an input floor at all origin points, and the state states are the densities for all links. In our model, our aim is to minimize the total time. For the dynamic formulations, first, we need to create a dynamic for each link, and then we need to consider how to connect each link into a complicated network. For the constraints, they include the constraints on density, floor, and the number of vehicles. I will just dive into the details of these parts in later slides. When you create a dynamic model in the traffic, the biggest challenge is the switched case. What is switched case? I will explain this concept by using a simple example. In these figures, you can see these contour lines represent the objective, and we want to minimize the objective. And this orange hyperplane indicates the constraint. And in the left figure, the constraint is smooth. So at any point of this constraint, the gradient continues. So whether you search from left direction or search from the right direction, according to the direction of a gradient descendant, you can always find the local minimum. But in the right figure, the hyperplane is not smooth. They are composed of two different hyperplanes. So at this point, the gradient of this point has two different values according to left direction and the right direction. So if you search from this point, according to the gradient of descendant, you can get to this point. But at this point, the model doesn't know the exact value of gradient because they are two different values. So the model doesn't know the direction of people improving. So it gets stuck here. So the solver will tell you, oh, the problem is not convergent. We cannot get your result. So this is a problem caused by the switched case, and we need to solve it. In our problem that I will explain in detail in later slides, because it involves the Jacobian of some formulation. So it must be at least twice continuously differentiable. Maybe you are not very familiar with the switching behaviors, but the switching behaviors are very common in real-world applications. I will just introduce two simple examples to help you understand this concept. The first example is smart thermostat. In smart thermostat, it needs to determine when to turn heating system on or off by considering some factors, including outdoor temperature, electricity prices, or occupancy. The aim is to optimize energy costs and maintain comfort. This smart thermostat is very common in some smart buildings. The second example is bipedal robot, which is very popular recently. For this robot, the model has two operating modes: stance with robot's foot on ground and swinging with robot foot in air. The model needs to determine when to lift off and when to touch down in order to maintain working space with minimal energy and prevent force. I just downloaded two videos from YouTube. So in the left video, because the model can capture the right moment of switch behavior, so this robot works like a real human. So it's very smooth. But in the right video, it's another story because the algorithm cannot capture the right moment of switching behavior. So when you optimize the switching moments, the robot falls down and roll over. So these two examples show it's very important to consider switch behavior when you want to optimize the whole model. in traffic area, such switch behaviors are also very common. In the dynamic model, in this slides, I will show the exact switch behaviors in traffic area. When you want to create the dynamic model for the whole network, first you need to create the dynamic for each link. This is we split each link into many different cells and create a dynamic formulation for each cells. And this is the formulation for the density change of each cell. So when you create the one link dynamic in traffic area, people usually use Goodenough numerical scheme, also called CTM, which is a switch case. So you can see this capital F is the flux across the boundary of cell. So in the CTM definition, this flux has different values based on different conditions. So this is a type of a switch case. This is the situation that we want to avoid when we plan to use gradient-based optimization method. So in order to solve it, I use less better rich numerical scheme here, which has a consistent formulation as defined by this formulation. And in this formulation, the F function is a floor density relationship. We also call it a fundamental diagram in traffic area. I use quadratic function here. So for each point defined by this function, the gradient always exists and continues. After create a dynamic formulation for each link, we also need to consider how to connect each link into a complicated network. So we need to use merge model to determine the transfer flow from YIL and YJL from upstream link I to downstream link L. And the definition is as follows, which is the middle value of three variables. And in this case, in this definition, the SI and RI links demand function and the supply function. And the PIL is a probability that the downstream flow comes from upstream link I. And we can define it as a 0.5 for the later application. And we have already solved the switch case appeared in one link dynamic. For the merge model, there are also two types of a switch case. The first type of a switch case comes from the definition of SI and RI. I just write the definition of SI here and also draw the corresponding floor, first derivative and second derivative of SI. And so you can see for the second derivative, at this point, row head, the second derivative non-continuous. So for the model, it doesn't know the exact second derivative at this point, row head. And we need to solve it. How to solve it? I use Heaviside approximation. In Heaviside approximation, it uses a smooth curve to connect two values, 0 and 1. We can use a similar trick to use a smooth curve to connect the value of F rho and Fmx. So the switch case caused by the definition of SI have solved. And for the RI, we can use a similar trick. This is the first type of switch case in merge model. And this slide shows the second type of switch case in merge model, which comes from the definition of YIL. This is the dynamic formulation for the orange cells. And you can see the YIL is a middle value of three variables, which is a switch case. By considering different conditions of these three variables, we can get the different values of YIL and YJL. Such results can be shown in these two figures. For example, if the sum of SI and the SJ is smaller than RL, and then the value of YIL and YJL is defined by this blue point. We can also use a three layer structure, tree structure to summarize all possible solutions of YIL and YJL. For example, if these three start from this point, if these three conditions are satisfied as simultaneously, and then we can get the exact value of YIL and YJL as follows. And this three layers tree structure summarize all possible values of transfer flow YIL and YJL. So it also shows it is a typical switch case and how to solve it. I use vibrational inequality framework to solve it, which can changes or switch the condition into another mathematical problem with equilibrium constraints. And then we can solve a nonlinear optimization method. We can start from a simple example. In this example, dot x equals to sine fx. We let lambda equals to sine fx. Based on different conditions of fx, lambda can get different values. And then by using vibrational inequalities, we can use these continuous formulations to replace this if-else statement. The BL and B up equal to -1 and 1 sequentially. For example, in this case, lambda equals to -1 and fx is larger or equal to 0. We can use this to, I can prove this for you. If lambda equals to -1 and then this formulation is always 0, but for this formulation, this part is a positive. So eta must be larger and or equal to 0. Eta is equal to fx, so fx must be positive and or equal to 0. So we can see that this case, the first case, can be represented by these formulations. And the second and third case can also be represented using the similar improvement. For our dynamic formulation, which is more complicated than this simple one, and the switch case is three layer tree structure, which is also different from this one. This one is a one layer structure. But we can still use a similar trick. The only difference is the lambda and the f row in our application is a vector of 4 variables. But in this case, the lambda and fx are just 2 values. So by using vibrational inequalities and introduce some auxiliary variables, we can change a switch problem into a continuous one. Though the number of variables are much more than the previous one, the problem becomes tractable. Okay.
Just a question, also, besides having more variables, do you get bilinear constraints? So for example, in the variation inequalities, the box to the right. So lambda is now a variable and eta is now a variable?
Yes.
So you have this bilinear term lambda times eta?
Yeah. You mean this one?
Yes, the third and fourth.
Yeah. These are equilibrium constraints that are introduced by using vibrational inequality framework. By introducing auxiliary variables, we also introduce some formulations to constrain these variables to make sure our new continuous formulations can replace the if-else statement, the switch case caused by the if-else statement.
Okay.
Not only variables, also constraints are also introduced. After explaining the complicated concept in a mathematical model, I also want to explain the definition of objective here. our objective is to minimize the total time for all vehicles in the simulation. It includes two parts: the waiting time for all vehicles in the origin points and the moving time for vehicles travel on the road. You can see the U is the input flow at a corresponding origin point. So the integration of U corresponds at T corresponds to this red dashed line, which means the number of vehicles that have already departed this origin point. And the CI is a predefined number of vehicles departing from origin point I. So the difference between them is corresponding to this part is a number of vehicles which still wait at the origin of when times T. And then we can do the integration from T0 to TF and do the summation for all origin points. In this example, there are only 3 origin points. And then we get the all vehicles waiting time at the origin point for the whole system. And for this part, the multiplication of Li, Lij, and rho Ij. L is a length of cell J on link I, and rho is a density. So the multiplication of them means the number of vehicles in cell J of link I. And then we do summation for all links and all cells and do the integration for the total simulation time. We can get the travel time, the moving time for all vehicles in the system. Because in later we apply this model in file evacuation case. So we add 2 weight Wi and Wx here to control the priority of vehicles. For example, if the phi occurs here and this origin point is closer to the phi ignition point, so we want the vehicles departing from this point to have a higher priority to make sure they can leave the dangerous area as soon as possible. But for vehicles which are far from this ignition point, we can give them less priority. So it means they are still safe if they cannot leave their origin point very quickly. And we will share the results caused by this different setting of weights in later application section. And then by combining all the objective dynamic formulations and some constraints, we can get the whole model. And then we calculate the Lagrangian and the corresponding KKT conditions of the problem. And finally, our aim is to make this metric close to 0. We use internal point method to solve it. Okay, we have finished all the complicated mathematical part, and then we can see the application. First is an example case, because Professor D'Agostino has already provided an analytical solution for a simple network, but they didn't provide an analytical solution for a complicated network. But our model can solve both the simple and the complicated network. In order to compare our results from their analytical solution, I just use a simple network provided in his paper. And in this case, I draw the density evolution for these 2 links. And you can see our proposed model match very well with their analytical solution. The only differences occur at some states where density change sharply, but it's very reasonable to understand because our model use numerical method to solve it. If data x and data t are not as small as possible, it cannot capture the sharp change of densities. And we also compare our controlled result with uncontrolled solutions. So you can see for each link, our controlled result can make the density of link returns to 0, maybe 1 hour earlier than that on the uncontrolled solution. So our result can save time for the all vehicles. And we also apply it in a real case, inverse in the Western Marine of California. This is a very rural village, and all vehicles are living in this these red points, and this is their local residents' home, and this village has a special geographical attribute that is one way in, one way out. When the fire occurs here, they must pass this point, and then they can go to different destinations. So it's very easy for this link to be congested. So this link face high pressure of congestion. And based on the historical data, we assume that the fire ignition point here, and so so in this case, the origin point 3, 6, 7 closer to the fire ignition point. So in the later application, we assign vehicles starting from these 3 points with higher priority to leave the danger areas. And we also collect the data to get the two flow density relationship for 2 different type of links. This is the dynamic videos for the results. So you can see our vehicles start evacuating from their corresponding origin point. And it's very easy for this link to become congested, and the queue forms. And as vehicles get to the destination, the queue dissipates, and all vehicles get to the safe area. This is the results when origin points 3, 6, 7 has higher priority. I draw the evolution of input accumulation in this case, so you can see vehicles in these 3 points can depart their corresponding origins earlier than vehicles in other origin points. Maybe they only need half an hour to leave their corresponding origins, but in other case, they need 3 hours to leave. And then I also draw the density evolution for all links in this simulation under the same case, except the optimal control, the results from optimal control model. I also input the control calculated from our model into a microscopic simulation software Sumo, because I want to see whether these 2 type of simulation method can get similar results. Because I think the real traffic vehicles movement can be closely captured by microscopic traffic simulation. And you can see the total trend of the density change are very similar. The only difference is that the microscopic simulation has so many fluctuations about the density, but it's very easy to understand because in the microscopic simulation, we just record the density for each link, the density caused by each link, caused by each vehicle. The resonance will caused by the movement of vehicle. But for the microscopic simulation, it just captures the aggregate behavior of all vehicles. I also did the comparison of all optimal control model result with another phased evacuation strategy, which is very popular in evacuation case. And we can only focus on the exit link density change. And the orange line corresponds to our result. You can see in our result, all vehicles get to destination 1.5 hour earlier than that on the other phased evacuation case. Okay, I have finished the first project. Do you have any questions? Okay, I will move to the next part.
We're trying to get the one.
Oh, yes, I was gonna say there was a question in the chat. But actually, sorry, it's from a few slides back.
Slide 8.
Yes,
Eight.
correct. He was asking, he said, correct me if I misunderstood, the switch case in the illustration B. It sounds for me that even though having two linear inequalities, which gives you two hyperplanes as constraint boundaries, falls into that scenario.
I will see. But I'm. Oh, you will only have two linear inequality.
If you don't mind, I can ask myself. Yeah, I can ask the question again. Can you hear me?
Yes, yes.
Okay, yeah. First, I want to clarify these constraints you illustrate, they are actually equality constraint. I think I misunderstood before. They are kind of like equality constraint. You are constrained to stay on those hyperplanes. Is that correct?
I don't think it's inequalities constraint.
So these are equality, right?
Yeah, which means you need to satisfy this hyperplane. You need to find the local minimum, at the same time satisfy this hyperplane.
I see. So that sounds like we should characterize it first as a non-convex optimization problem. Is that correct?
I think it is convex because the objective is convex. And
But
the
yeah,
Correct.
but the equality constraint is not affine.
I think the reason why I designed this parameter is to show that at the switch point, the gradient are not continuous, and to explain the concept of the problem caused by the switch case, and the switch case caused the problem failure, for the calculation failure.
I see. Yeah. Then that's my next question. Also, my last question. How do you define gradient in this case? I know we all understand how to define gradient for the objective, but I think what you are mentioning is you kind of like define gradient on the manifold of the constraint. I just curious how technically or precisely the gradient you refer to is defined.
I think you just draw a straight line here, and then the gradient is the ratio of this. It is a straight line, or the ratio is a gradient of this point. You just draw a line at any point that you want to calculate the gradient.
I think maybe if you can answer it, the gradient with respect to what?
Yeah. The gradient, for example, the gradient of this point is just you draw a straight line here, and then you use that mathematical concept to calculate.
I see. Yeah.
Thank you, very pedagogical. I appreciate it. I know we have a common collaborator, Louis Comfort. She comes from the policy world, and there is a whole set of uncertainties: who is going to evacuate, who has a car, etc. I'm very curious. This control of the density is kind of real time, and how do you implement that? It's like some traffic light through apps. So what you're assuming, the whole behavioral aspect happens. Then you know who is in the street, and you are going to control the density in the links. How you guarantee that control takes place? And this is my ignorance in the topic.
Good question. What you ask is what I reflect based on the first project. Because you mentioned it is hard to realize based on real-time information. Actually, this is the first point that I want to say. This model needs a large amount of time, 2 to 5 hours. So it is just an offline solve. Yeah, maybe because in this case, we already know all the residence information. So we can, and we may also know the number of fire ignition point. We can calculate all this in advance and then tell the local residents when to start evacuating to avoid the congestion.
So it's a control of the departure time, right?
Yeah.
But do we need the flow traffic theory to, yes, I guess so, right? Okay, tell me.
Yeah. If you don't have any question, we can move on. I think,
Yeah, we have 15 minutes left, so
yeah,
see if you can finish the second part in shorter time.
okay. For the first project, I think I'm satisfied with the model because it can calculate all different situations very stably. But I also have some reflections based on it. First, it requires a large amount of time, 2 to 5 hours. So it is computationally expensive and less suitable for real-time application. So it is just an offline planning solver. Second, it's difficult to capture and incorporate the straightforward physical information, but this information is very essential for later control and optimization. Because as I explained, when you establish the model and then you use numerical method to solve it, what you finally solve is just a metric. So it's hard to extract some physical information from this metric. You just regard it as a mathematical problem. Third is that you spend most of computational time for strict convergence criteria, which then lead to meaningful practical improvements. For example, when you want to improve the norm of a metric from 10 to -3 to 10 to -4, the only difference maybe assign the right time changes from 30 seconds to 30.01 seconds, which is not noticeable from the practical point of view. So if you are a traffic engineer, you don't want to spend the time improving something that not have practical improvement. So all these reflections led me to improve it in the design of my second project. So in the second project, link-based mixed integer linear programming for traffic signal control, I just use a semi-analytical method, which is much faster than this numerical method. And you don't need to model within link. You don't need to split the whole link into too many different cells and solve it. And the only thing that you know is the input flow and the output flow and the boundary. With this information, you can calculate the flow and the density at any point at any time by using the analytical solution. So it's much faster than the numerical method. So you only need several seconds for large-scale traffic simulation. And you can also extract the physical information here because the road, the flow, and the density are two types of important physical information for our later control and optimization method. But this physical information is hard to extract for traditional numerical method. Third, this method can also avoid vehicle holding problems. I just list some simple mathematical models here. This is a traffic flow model. And then the capital NTX is an accumulation of vehicles at any point and at a point X and at time T. So I define the derivative of capital N with respect to space as a density rho, and the capital N the derivative of N with respect to T as a flow. And then we can replace the density and the flow by using these two formulations, and then we get the Hamilton-Jacobi equation. The smart mathematicians have already found the Lex-Hopper formulation that can solve this Hamilton-Jacobi equation. So by using this formulation, we can directly calculate the capital NTX at any time, at any point. And then we do the derivative with respect to space and the time to get the corresponding density and the flow. And this density and flow are very important for our later optimization. And for this part, I will skip all the mathematical parts and only focus on two formulations. In this formulation, it shows that we can capture the Q spillback behavior caused by the red time signal. And then in this case, it describes the wave dissipation process. So it means when we assign green time after the red time, the previous formed Q can dissipate later. I designed a simple case here. In this case, there are two intersections, and all vehicles from these origin points often move to the one exit point. So it's very easy for this link to be congested. And you can see in uncontrolled simulation, and the congestion for this link is very serious. But in controlled strategy, by using the real-time information, by detect some physical information, and by knowing the upstream travel demand, we can adjust our traffic signal at the real time. So the congestion situation in this link is much less compared to this one. And in order to explain why the congestion is so serious in uncontrolled case, I also explain these two figures. The upper figure corresponds to density evolution of link 4 of intersection 1, and this part shows whether the input flow for link 4 comes from upstream link 1, 2, or 3. So in this case, you can see always the input flow always comes from link 2. So it's very easy for vehicles from link 1 and link 3 to be congested, which can also corresponds to this case that the vehicles from link 1 and link 2 will be congested here. But in the controlled strategy, all upstream links have the same priority, same opportunity to move to next link. So the congestion released in controlled strategy. Okay, I have finished all the work that I did during the PhD, and next I want to share my thinking about future work. I think in traffic area, the innovations come from two parts. First is the dynamics, based on different scenarios, based on the problem that you are interested in, which means the research objective, based on different communication method, communication range, communication distribution method. You will define different dynamics. So this dynamics is one type of innovation in traffic area. The second innovation comes from optimization method. Except the optimal control model that I explained in the first project, the model predictive control is another traditional method in control area. And recently, the neural network based optimization method is also very popular. So based on these two innovation parts, I will propose three directions that I'm interested in the next phase. The first is a platoon control and dedicated land management direction, which focus on each vehicle and try to optimize internal spacing, string stability, and the headway between vehicles. And it is aimed to reduce traffic oscillation and collision risk. So for this direction, its focus is each vehicle. And for the second direction, they want to control or connect an autonomous vehicle to regulate the whole traffic. So their focus is to regulate the whole traffic flow. It is a coupled PDE ODE model, and use ODE to describe the connected autonomous vehicles dynamics, and use PDE to describe the whole traffic flow dynamics. Then by considering different levels of corporations, like centralized or decentralized, they can get different results. This is the results shared by Professor Maureen Lauren, maybe 1 year ago with me. And you can see the up figure correspond to uncontrolled case. So in uncontrolled case, the congestion covered by the red area is very serious. Then by introducing some connected autonomous vehicles, the congestion area is much less compared to uncontrolled one. And the third direction is about the optimization method. Except the traditional model predictive control method, the reinforcement learning method is also very popular, which is suitable for the case where the model is unknown. And so the reinforcement learning method can mimic the model's dynamics by interacting with the environment. But it's hard to satisfy some constraints. In traffic area, I think most previous researchers have already provided very accurate traffic dynamic for all types of traffic simulation, whether it is micro or macro, whether it is for each vehicle or for queue of vehicles. The dynamic model is already known. So in this case, maybe the neural network-based optimization method is more suitable because it can satisfy some physical constraints, but it also has some memory intensive problem for training. Yeah, that's all. Finally, summary. In today's presentation, first I introduced the optimal control model in my first project, and next I share my second project about the link-based mixed integer linear programming method. And for my future work, I just propose 3 directions that I'm interested in and want to explore in my next phase. That's all. If you have any questions, so feel free to ask.
Questions?
You mentioned in your motivation case that the first project you did would be applicable for changing the state of a robot. Then I wonder, when you talk about the innovations of your expertise into transportation, if you would consider the change in a state of an autonomous car when something dangerous comes to it. That would be super innovative. And I think you have the theory to handle that. How to give, because I'm being the bad cop here, it's like what you mentioned as innovative in traffic. I've seen like Cathy Wood, they have her whole tenure tracking reinforcement learning for traffic. Maria Laura is doing what she's doing. Then what you mentioned innovative, perhaps is innovative fast, no? But imagine you can control an autonomous car with the same theory you apply as a. Is that possible?
Yeah, yes. You mean the switch case is not occurred in traffic flow, but occurred in autonomous vehicle, correct? I agree, because the switch situation is very common, and in a vehicle-based control, there must be some switch case. So it is also the work that we can explore in the future.
Fantastic, I think.
Yeah. And I also saw some other researchers did the similar work about the switch case in vehicle-based control.
Probably, but
Yeah.
you would bring your expertise in traffic,
Yeah.
controlling
Yeah.
the dangerous cases
Yeah.
for the car.
This is also a very popular topic. I think there are
I know.
many researchers did it.
Oh, there's one more question here. Excuse me, he's asking, can you give us a sense of the scalability of your methods? What are the sizes of your?
Good question. Maybe I can speak this the question from EG. Can you give us a sense of the scalability of your method? What are the sizes of your experiments? Ideally, without any technical constraints, how large scale you would like to study? He mentioned the scalability of the problem. I think the one method that can solve the scalability is the ADMM method. You can split the whole network into many different parts, and then use ADMM method to solve the connection between different subgroup. I think this is the one method that is very popular to solve the scalability issue when you want to extend your current problem into a large scale. Hello, yeah. Are you satisfied with my?
Oh yeah, yes. Thank you. And I think a part of my question is just to get a concrete sense of currently what's the size, because you presented two study. What are the size of them respectively?
For these two methods, the size are different. For the first method, currently maybe 20 or 30 links. I have tested the simulation in the case with 20 or 30 links. But for the second project, I think the area is larger because the second method is analytical method. We don't need to solve the dynamics within link. So for the second project, I have used it to solve larger area. I think for the area for searching number for links, the calculation time, and for 1 hour simulation, the calculation time is just 1 or 2 seconds. So because for the second problem, you only need to the boundary floor. So the number of variables is very small, even for a large network. You only need to consider the connector of
What large means how many traffic lights? How many intersections?
How many intersections? I think it's maybe 20 or it's not so large, but the calculation is very yeah, this here is the calculation is very fast.
Yeah, thank you. And I think the last part of my question is solving for larger larger problem a pursuit of your future work? If so, how large the scale you want to extend your method to, or use new method to solve?
It depends on requirement. It depends on real scenario. How large? I think currently, because especially for a second project, I still consider the specific traffic light assignment, like the Q formulation, Q dissipation. If you consider a very large scale simulation, currently you don't need to consider too detailed simulation of a traffic signal. You can use approximation method to get the flow transform at such intersection. So if you want to consider very large scale simulation, like the simulation for California or even for the US, sometimes you don't need to consider so much details about how the traffic signal will cause the Q formulation or Q dissipation. Yeah, it is a balance of resources when you want to scale it into a large problem.
Thank you. Yeah, thank you for your answer.
Yeah, thank you for the question.
I have a question before we end, which is on the first part where the main idea was you've got these switch statements that can look like if else statements in your model. This idea to use variational inequalities to be able to solve these or compute and simulate the models. how have people addressed that problem in the past? I think you spoke a little bit about it. And is your idea to use variational inequalities new? How is it new?
I think previously, previous research have already used variational inequalities to solve the switch case. But the previous result just use one layer structure, just if A and then if B and then. But in my problem, I don't know whether you still remember, there's a 3-layer structure, 3-layer tree. So in this problem, I just extended from a 1-layer tree structure to a 3-layer structure. Yeah. And if you extend to a 3-layer structure, there are also some constraints that need to be adjusted. And yeah.
So does that mean you have just a dramatically more complex variational inequality, or is it straightforward? Like, sorry, let me back up. Why is it difficult when it's 3 layers? Yeah, what about that is difficult?
In 3 layers, you need to satisfy some conditions at the same time.
Yeah,
But if it is just 1 layer, you only need to satisfy one condition. But the combination of, for example, 3 conditions sometimes may cause overlap when you consider the combination of these conditions. You need to avoid such overlap and also to make sure that all these conditions consider all possible situations in this case.
okay. And you know, ultimately, does that mean that it's harder to reformulate? You know, all those switch cases into variational inequalities, like how does that difficulty manifest in your modeling?
I think it's
For to say that another idea, what is your key idea to address this complex 3-layer structure?
key ideas.
Yeah.
I think it's just by introduce some auxiliary variables to make sure that all these possible conditions can be satisfied. And there are no overlap between each conditions. For example, how to get y this transform flow by combining this probability, because the algorithm of this situation is the probability of these 3 variables, and how to combine this probability with the lambda defined by how to combine the probability with the lambda, how to find the relationship between them to make all these different constraints can be connected with each other.
Okay.
Just how to design some constraints to make sure that if else statement, the complicated combination of this if else statement can be represented by a continuous systematic formulations. To make sure they are the same, so that they can even if you solve that part, you can get the same result.
Great. Okay, this helps. Any other burning questions? All right, let's give her a hand. Thanks,